Okay, so I hope everybody is doing well. Nice to see you all. So today we'll work on our kind of first method for finding exact solutions to differential equations. So we're going to do some integration today. That was kind of the point of some of the reading problems that you looked at. So we're going to be working on worksheet 5, dealing with separation of variables today. But if you had a chance to think about this one, so this was on your reading quiz as well. If I want to evaluate this one, and feel free to chat in or just speak, what method of integration would work here? Integration by parts or substitution?
So on this one, I originally used substitution, but I got it wrong.
Yeah, and so some people are also suggesting substitution. And so just as a way of thinking about these, substitution kind of undoes the chain rule, and integration by parts, I'll just abbreviate it like this, kind of undoes the product rule. And sometimes it's hard to tell these two methods apart because when you use the chain rule, you actually get a product out in the end. So oftentimes these are applying to products. But if we're trying to do substitution here, probably what you might think of trying is let u equal the power of the exponent. So when we identify w or u or whatever it might be, we're trying to identify what is the inside function of the original function. So it makes sense that we would look inside the exponential and say, it looks like 2x seems like an inside function. So let me see what happens if I try and do this. So I would have x e to the u dx, right? I called it w, so I'll put a w here. So I would replace the 2x with w. And now I've got still some x's left. And so the idea is we would hope to get rid of the dx term by replacing it with its equivalent for dw. And so if I try and do this replacement now to get rid of dx, I could write this as 1/2 x e to the w dw, right? I could replace dx with 1/2 dw. But we kind of have hit a dead end here. I don't know what to plug in for x, and you might think like, okay, well, I can use this relationship to get rid of the x. I could replace x with 1/2 w. But I essentially got back the same integral that I started with at this point. So I started with something that looked like this, and I pretty much have something that almost looks like that again. So we would hit a dead end at this point. So substitution using w equals 2x isn't going to be the most direct way of doing this. It might shoot us into a loop. Any questions about that? Why that substitution didn't quite work out?
Yes, I believe I arrived at the correct answer using this. I was just gonna.
So the idea is what would be the best way to do it, okay? And so if we do it this way, we're pretty much back to where we started. We just have 1/4 times the original integral that we started with. So we really haven't made progress. At this point, we would want to use integration by parts. We could have just done integration by parts from the very start. So there's no need to do substitution at all in this problem. And I don't think it helps make it more efficient. I think it just takes an integral and rewrites it in a very similar way. So if you get into a loop like this, and now I look at this and I say, well, how can I integrate that? And I don't know, then you can try another substitution or perhaps another method. Substitution is going to work if, for example, instead of 2x, I had a 2x squared up here. That might work. What you would like to see is that the inside function and this multiple in front, somehow they're related through a derivative. But that's not the case here. So instead, let's try integration by parts on this one. And so different ways that you might write this out. But I've got this integral, and I would like to write it as a u times a v. So the idea is one of these terms is going to be u, one of these terms is going to be dv, right? And we need to figure out which is which. And usually the idea is you would want to pick u so that when we take the derivative of it, it gets simpler. And we would want to pick dv so that we actually can integrate it. And so putting an x over here and e to the 2x over here, right, to figure out what v is, we would integrate dv, and that would give me 1/2 e to the 2x, and we don't need to worry about the plus c at this point. And then what you hope to get after thinking about this is, will we be able to integrate u prime v at this point? And if you can, then it's going to be a success. And if you get an integral which is worse than the one that you started with, then you might want to try and flip around what you tried for u and v. But in doing this, then integration by parts tells us we could rewrite this as u times v times the integral of u prime v. So we've got u is x, we've got v is 1/2 e to the 2x, and then we would subtract from that the integral of u prime, which is just 1 times dx, times v, which is 1/2 e to the 2x. And then we're good because we could actually integrate 1/2 e to the 2x. And there we would get our solution. So I just want to kind of go through these mainly just to point out that this was stuff from Calc 1 or possibly Calc 2, depending on how things were broken up. Some of you might have taken Calc 2 very recently, and this is very fresh in your head. Some of you might have taken Calc a year or 2 years ago, and this might not be as fresh in your head. It's really important for you to go back and review integration. To solve differential equations, we're going to have to be able to integrate. And it's going to be really hard to be learning the integration on top of the new methods that we're discussing. So I think before the class gets too far along, this is a really good point for you to identify how much work you need to fill in some of those gaps from calculus. So I did put some practice materials up online if you want to practice integration by parts, substitution, and we're going to talk about another method very soon called partial fraction decomposition, which is going to be really important. So that's something that you might not have learned in Calc 2, a method called partial integration by partial fraction decomposition. So I put up some materials on that too. That would be good to review. Someone asked about, is trig substitution going to be important? Not as important. It's possible it comes up once or twice over this semester, but it's not as frequently used as, say, integration by parts or partial fraction decomposition. So it doesn't hurt to review trig substitution. I just don't emphasize it because it's not going to come up as much as some of the other methods. Okay, and so yeah, if you do want some extra help with this, I'm happy to meet with folks at some other time. I just don't want to use the time in class to be going back over the integration, since people are at different points. So I want to use the time we have together for things that are going to be useful for everyone. But I'm more than happy to spend some time reviewing this for those that might need it. Okay, so any other questions? Okay, so on the reading or the video, or in section 1.1 of the textbook, they talk about kind of the first sort of differential equations that we can solve. And these would be first order differential equations that only depend on the independent variable. So differential equations that look something like this. And in other words, they're independent of the dependent variable. So keep in mind, this is not autonomous, right? Autonomous means independent of t. And so if we have a differential equation which doesn't depend on y alone, then these are just antiderivatives, right? That you've already talked about in calculus. This differential equation is just asking us, can you find the function y whose derivative is 6t squared? And we don't need anything fancy to think about what is a function whose derivative is 6t squared. We could just find the antiderivative of that and say, okay, 2t cubed would work. And then we want to describe what would all possible functions that have derivative 6t look like. So that would be this over here. Okay, and this we call a general solution. Okay, and so general solutions are families of functions that describe what would all possible solutions have to look like. So there are infinite number of general solutions to a differential equation. And just to find some space, so if we're trying to sketch the solutions to this, we had t and y. And what we can see is that our solutions are going to look like cubic functions. So they're going to look like things like this and various shifts of that. So all of these functions, for example, would be possible solutions to the differential equation. Notice they all have the same slope generally. We just shifted them up and down. And sometimes, in addition to that, you're given an initial condition. Okay, so for example, if in addition to this differential equation, we had some initial value given that at time 2, y was equal to 10, then we could go ahead and plug this initial condition into the differential equation, or into the solution for the differential equation, the general solution, and solve for the value of c. And this over here is what we would call a particular solution to the initial value problem. So initial value problems have unique solutions. And the equivalent of what we're doing there is we're pretty much saying maybe there was our point that we were given that at time 2, the output was equal to 10. And this is actually not the right curve, but then what we found is the value of c that corresponds to that. And then we get a unique solution like this one. Okay, so that's kind of one big picture that's going to be with us the whole semester long, is that when we're solving just a differential equation with no initial condition, we should get an infinite number of solutions that will have one or more arbitrary constants in it. When we have initial conditions given to us, then the solution should be unique. We should be able to find exactly what those constants need to be in order to guarantee our solution goes through the right points. Okay, so any questions about that sort of material? Okay, so then let's now think about how we could use this to try and solve like an autonomous differential equation, say that looks like this. So now the difference is on the right side, rather than have a function of t, what we're saying is that this differential equation only depends on the dependent variable y. That's what it means to be autonomous. And so if I want to solve this differential equation, we can think about trying to do what we did up top, which is, well, why don't we just integrate both sides of the differential equation? And so if we look at A, over here, if I want to solve this differential equation, what happens if when I integrate the derivative of y with respect to t, when I integrate that with respect to t?
Should just become y.
Yeah, so exactly, thank you. These are inverse operations, right? So they undo each other. So if I take the derivative and then integrate, I should get back the same thing. So on the left side, that's no problem. I actually would get y is equal to, and that's great. On the left side, the problem here is I would like to integrate y, but this is telling me to integrate it with respect to t. And since the whole point here is we don't know what the equation for y is, we're unable to evaluate what this integral is going to be. Right, so integrating that doesn't give me 1/2 y squared because that is an expression of y, but we're supposed to integrate with respect to t. So we can't just do the same exact thing that we did up top because now our expression has y in it and not t. And if we were to try to do the setup in B, it's kind of the reverse issue. So here, what's happened is we changed the dt's to dy's over here. So integrating with respect to dt didn't work. Let's integrate both sides with respect to y. And that would be okay on this side. I certainly can integrate that with respect to y. It's just that if I am integrating y prime with respect to y, these operations are no longer undoing each other because the derivative is with respect to t. And so if I integrate with respect to y, there's a difference there that is not going to undo each other. So that one is not going to work. What about C? Does anyone see an objection with the method in C?
How do we get dt and dy on the other side? I get if like the last two we were multiplying each side of the equation by one thing, that's okay, but there's a dt on the one side and dy on the other side. So how do we?
That's right. So when we have this equation like dy dt is equal to 0.2y, this was given to us, right? We start with this equation. So it's an equation. As long as I do the same operation to both sides, we're not going to lose that equality. So in parts A and B, we actually did the same thing to both sides. We integrated with respect to the same variable on both sides. So there's nothing wrong with that other than we were unable to evaluate some of those integrals. In part C, the issue here is we're doing different things to each side of the equation. We're going to integrate this side with respect to t and that side with respect to y. These are different operations. So that method, we can't just integrate it quite like that. So the point being is we need some more methods to solve differential equations. We've run out of ideas of just simply integrating both sides. Any questions? Okay, so let's take a look at this. Same differential equation, I just called it P instead of Y so that we can attach some meaning to this. And we'll kind of go through how we can solve this step by step below. But I want to kind of start with a little intermediate step that might help us. And that is, let's say we want to calculate the derivative of natural log of P with respect to T. And so this would be similar. So does anybody know how that would work?
For the derivative of the natural log of P,
Mm-hmm.
it's just 1 over P.
Yep. So be careful in that right? If I take the derivative of natural log of P with respect to P, I would get 1 over P. In this case, we're taking the derivative of natural log of P with respect to T. So that's why we have like a chain rule. So you did the equivalent of like saying the outside function is natural log and the inside function is P. So we take the derivative of the outside function, 1 over P, and then what are we missing over here?
dt.
Not a dt.
dp dt?
dp dt, yeah. Right, and so this might look familiar from implicit differentiation. Implicit differentiation is just the chain rule. We took this expression, we broke it up into an inside function, which is P of t, and an outside function, which is ln of P. So then we took the derivative of the outside and then multiplied by the derivative of the inside. And since we don't know what P is, we just say the derivative of the inside function is dp dt. So this is going to be really the key to unlocking how we're going to solve this particular differential equation. Okay, any questions about that? So if you're kind of keeping a little log of things in calculus that might be good to look over, I would include implicit differentiation in with the integration stuff. Okay, so then let's try and solve this, and let's kind of follow the steps as they're laid out here. And the equation that we're trying to solve is this one right here. So we start with this equation, and you know the key here is the same as algebra. As long as I do the same operation to both sides of the equation, we're okay, right? I can do whatever I want as long as I do the same thing to both sides. So this method is saying, okay, let's start by dividing both sides of this equation by P. Okay, wonderful. That so far so good. And sorry, can you guys hear my cat way over there? I thought you couldn't, and then I listened to my recording from the last class, and I'm like, nope, that mic picks up the cat. Very impressive. Okay, sorry, she's done. All right, so now the whole point of doing that first part is, and this is maybe not something that you would think of off the top of your head, but you can say, 1 over P dp dt, this is exactly the derivative with respect to t of the natural log of P. Right, and that's what we saw up here. So I'm just going to replace the left side with the fact that 1 over P dp dt is equal to the derivative with respect to t of natural log of P. So in this case, I've just rewritten the left side of the differential equation, and I haven't done anything to the right side. And now the operation that we're going to do is we're going to integrate both sides, say, with respect to t. And so on the left side, we're going to integrate the derivative of natural log of p. And on the right side, yeah, we're going to integrate 0.2. Okay, but the important thing here is we're integrating both sides with respect to the same variable, so we're okay here. And now we're in a situation where we can integrate both sides with respect to t. So on the left side, I want to integrate the derivative of the natural log. What would I get when I integrate the derivative of the natural log?
Natural log?
Yep, exactly. These are going to undo each other, and all that we get is natural log of p. And then on the right side, we've got 0.2 times t plus some arbitrary constant c. And then in the end, what we want to get is ideally an equation for the solution. Like I hope to write this as p is equal to some function of t. So now we can try and solve for p. So how can we solve for p? Any thoughts on what I can do to both sides of the equation?
Put in an e.
Yeah, let's take both sides and raise e to the power. So I'm going to put an e here and an e over here. Right? Again, if natural log of p is equal to 0.2 t plus e, then raising e to those two things should equal each other because the powers are the same. And now the point of doing that is what do I get when I take e to the natural log of p?
P.
P. Okay, just like derivatives and integrals are inverses and they undo each other, the same goes for exponentials and logs. So we've got one solution that we could leave like this, and this would be totally fine. I will just say that our solutions normally for something like this is like an exponential model for growth. We can rewrite it. Usually we like to write it as an exponential function more directly like that. So here we could just use the property of exponents that say when I have addition in the power, it's the same as multiplying those two things times each other. And then what we can say is that if c is an arbitrary constant, then without any loss of generality, right, e to the c is also just some arbitrary constant. So we more commonly would write this as a formula like this. And then it's never a bad idea to go back to the original differential equation and plug this in and make sure that it works. And that you guys have to do on the first assignment. You practice how you check whether a solution works or not. So when you're at home and if you've got some time, I think it's definitely good to make sure that your solutions check out. Any questions? So this is a general solution because we did not have any additional initial values given to us. But you may recall from exponential families of functions that this k is telling us the initial value, right, the y-intercept. So you can see given some condition, that's going to determine what the value of k was. And then we would get a unique solution.
Question.
Yep.
On the first step,
Mm-hmm.
you have we have 1 over p dp dt equals 0.2.
Mm-hmm.
And I find the d dt ln of p step kind of confusing. So I was
Yeah, so
wondering.
that came
instead-
from this scratch work that we did up top.
Yeah, I know, but it's like scratch work in the middle of a problem. It's like I need to know something different for another problem. So I was wondering if you could multiply dt. You know how dp dt looks like a fraction? I was wondering if you could multiply each side by dt to cancel out the dp dt in the bottom on the other side, and then it'd be 0.2 dt. And then once we have that, we have I don't know if that makes sense, but then we'll have dp on the left side and dt on the right side, and those match the variables that we are looking at.
Yeah, so to answer your question, which was initially, can I multiply, or at least after that first step, can I multiply both sides by dt? The answer is no. And then the addendum to that answer is, but that's what we're going to do anyway. So yes and no.
So it's not like right math. This is
It's
the
not
right
right math. That's right.
but it's right. We can solve it that way.
Yeah, we're moving in that direction. Yeah. Yes. Mathematically speaking, yeah, in the concept of multiplying both sides by dt is not correct, because dp dt is not a fraction. It's representing a derivative. It's representing a function itself. So technically, no, we're not allowed to do that. Yeah, just hold on to that question for a second. Yeah, and I think that's right. It's hard to, if we didn't do that step above in part A ahead of time, I think, yeah, it's probably not easy to see how do you go from this to here. That maybe that's not the most natural thing to do, to realize, that's the implicit derivative of the natural log. Yeah. Yeah, so we will try and streamline this a little bit. Any other questions? Okay, so let's now apply this technique to a differential equation that depends on both variables. So we've got dy dt is t over 3y squared. Now we've got t's and y's in here. So let's say first step is I'm going to move my 3y squared to the other side. I'm going to multiply both sides by 3y squared. And so let me just say, at this point, what I'd like to do is the same thing that we recognized in the previous problem, which is 3y squared dy dt. That looks like it should be the derivative of some expression of y that we would get implicitly. So does anyone know what could go inside those parentheses, so that when I take the derivative with respect to t, I wind up with what we started with up top?
Y cubed?
Yeah, y cubed would work. So it's really, all we really need to do is think about what is the antiderivative of 3y squared, right? We want to find the outside function here. So we could recognize that is the key step there. And now once I've done that, what would we do to solve for y? So what did we do back over here? After we identified that this is actually a derivative of natural log of p, then we went ahead and we integrated both sides, right? So the whole point of recognizing this as being a derivative of t is that now I can undo that operation, right? The whole idea is I want to solve for y. So we want to start undoing the operations that are being done to y. And this first operation that's being done to y is take the derivative. So let's integrate it. So we're going to integrate both sides with respect to t. And so on the left side, what would I get when I integrate d dt y cubed dt?
Just y cubed.
We get y cubed, right?
Yeah.
Because they're going to undo each other, right? That's the whole goal here, is we're going to undo all these things. And then on the right side, we integrate t, and we get 1/2 t squared plus c. And so we would call this an implicit solution because we haven't solved for y, but we can. The last step would be you would want to solve for y if you can.
So Professor, you may have just cleared it up with this last step, but I noticed you didn't put the plus c, the constant, on the left-hand side. Is that just convention right after integrating on both sides, you only put the plus c on one?
Yeah, I mean, you could put it on one side or both sides, but you know, if you had a plus c on one side and you had like a plus d on the other side, and you want to solve for y, the first thing you would do is like subtract c from both sides, right? And then you have arbitrary thing minus arbitrary thing, so you would just say, I just get one arbitrary thing over here. So you certainly can do that, but eventually you would just get to the point where you just have one arbitrary constant on the right side. Yeah.
Say this, we were given an initial condition
Mhm.
and we want to solve for C. Could we solve for C in the implicit and the explicit solution?
Yes, you could solve for it. You can use those initial conditions at any point in your and any equation that you might have. So yeah, you don't have to plug it in to the bottom over here. You could figure out what C is over here. That's probably, if you plugged it into the very last step and you wanted to solve for C, probably the very first thing you would do is cube both sides anyway and get back, you know, move back up to the level above. Yeah, so I think the question here is, like, does it matter where we plug the initial condition in to solve for C? It really doesn't. What you do want to be careful about is that plus C has to be inside the square root, right? Because we have an expression on the right side, and then we should take the cube root of the entire right side of the equation. So if you have the plus C outside of the square root, that would be incorrect. But in this case, we could solve for y. And so when we can solve for y, we call that an explicit solution. Okay, and that means we have written the solution in the form y is a function of t. And so when you can do this, that's desirable. You should always take it as far as you can go, but just be aware you're not always able to find explicit solutions. If I had y squared on the left side, I wouldn't be able to solve for y, for example. So on the homework that is due for Monday, some of the problems I say very clearly, be sure you give me an explicit solution. And in those cases, if you stopped at this stage, that would not be full points because that's not an explicit solution. You would be expected to go one step further. So just be aware of that.
Just to clarify here, if I ask something. So when we went from 3y squared to d dt y cubed, the reason we don't take the integral in the previous step is because when you take integral of dy dt, that doesn't cancel in the same way. Is that correct?
So if we try to integrate at this stage over here, let's say we do, and we would need to do the same operation to both sides. So the problem with doing this is that I actually can integrate this, but I have no idea how to integrate that with respect to time.
Okay.
Yeah.
Thank you.
Yep. Yeah, so that's the stage where we would do it. So really what this method is doing is it applies to very special situations where after we group all of our y's and dy dt's on the left side of the equation, we can recognize that as the implicit derivative of something. And that's not easy to do. So the question was, well, can I just take an equation like this one over here and just multiply both sides by dt and then bring the p over to the other side? And the answer is you can do that, but technically speaking, the manipulations that you're doing with the symbols are not mimicking mathematically what's actually happening underneath the hood. I'll just say that. So in practice, students separate things and it works just fine, but just keep in mind that dp dt is not a fraction. So we can't think of it as dp divided by dt. It's representing the rate of change of p. So there is some proof that's required to show why we can separate things the way we can. And the reading materials have explained it if you're curious. So let's revisit some of these problems and think about how we would do it, maybe the way that Abraham was suggesting initially. So I have this differential equation, dp dt is 0.2 times p. So the first thing we're going to do is separate things so that all of my p's are on one side and all of my t's are on the other side. So that means I would divide both sides by p. I'll do it in 2 steps. And then I want to group all of my t's on the other side. So here's where we're going to multiply both sides by dt. That's not exactly what's happening, but that's what the manipulation might seem like. So this would be the stage where we've now separated the variables. So on the left side, I have only p's. On the right side, I have only t's. And once we've done that step, now we go ahead and integrate both sides of the differential equation. And so the actual manipulations that we're doing here, things are a little bit fuzzy, right? One thing, dp dt is not a fraction, so I'm not just allowed to multiply that. The second thing here is at this stage, we're kind of doing different operations to both sides, right? On one side, we're integrating, and it tells me to integrate with respect to p. On the other side, it's telling me to integrate with respect to t. So there are some things I'm uncomfortable with, I just want you to know, but this is the way that people can do it. And so then we integrate the left side, which would give us natural log of p. I'll put an absolute value here because technically that's what we should get. And then over here, we would get the 0.2 t plus c. Yeah, and now we could exponentiate both sides. And yeah, I just want to make sure that when p could be positive and negative, when we integrate 1 over p, we usually have the natural log of the absolute value of p. Because we're working with a population here, p is representing a population, it's safe for us to assume that p is positive in this case. So in this case, we would get p is equal to e to the 0.2 t plus c, which matches what we got when we did it kind of the more standard, more carefully the way that we should do it. So in the background, what's really happening is what we did the first way around. But in the foreground, you can organize your work like this to help save yourself from trying to think of like, what is a function whose implicit derivative would be this? Okay, any questions?
Yeah. How did we turn the plus c in the exponent to a k in front of the e?
So this over here, we could write as e to the 0.2t times e to the c, right? So that's a property of exponents that when you have a sum in power, you can write it as a product.
Yeah. Okay. Okay.
Yep, and then that
Yeah.
e to the c is some arbitrary number that we'll just call a different
Yeah,
letter.
yeah.
K.
I got you now. Thanks.
Yep. Okay, any other questions? Okay, so let me just ask you all to try and do this one, the one that we already solved above, but doing it maybe in this more straightforward way of separating the variables. So try and use this shortcut that we just did for the previous differential equation. See if you can apply it to the 1 and 5 again. So these are generally like a 3-step process: separate, integrate, and then try and solve for the dependent variable. Okay, someone want to just explain what the separate phase would look like?
Sure.
Yeah, thank you.
So you take, you multiply both sides by 3y squared, and then you manipulate dt, but don't actually multiply it over to the other side, but you end up with t equals dt.
You wind up with t, sorry?
Sorry, t multiplied by dt.
Yeah, okay. Yep, so we're going to multiply both sides by 3y squared, and we divide both sides by dt. So now we've got this separated. Great. And so then the next step is to integrate both sides. And so over here we get the y cubed, and over here we get the 1/2 t squared plus c. And then lastly we solve for y. So point is, this method works. We get the same result either way. And in fact, the mathematics that we're doing is the same in both cases. In the previous way, we actually were essentially integrating 3y squared and t, right, to get the solution. We had to integrate two things, and those are the same two things where we have to integrate down here. We're just organizing our work a little bit differently. Okay, questions?
This shortcut is approved on like standardized tests and stuff?
This shortcut has my seal of approval, yes. So this is what's called separation of variables, yep. And this is, in practice, how people would do it, yeah. Yeah, so I think it's kind of a theme, maybe in all of mathematics, but certainly differential equations, that you can kind of streamline methods. Like you look at a differential equation, you identify what type of equation am I dealing with, and then I pick out what solution method is going to work for that differential equation. And so at some point we just start using these methods, but I do think that it helps the first time that we apply a method to just motivate, like, okay, what actually is this method doing? But once we kind of sum up that motivation, then you're free to use it without having to prove it every single time. Yeah. Okay, so yes, so this whole process is what's called separation of variables. And so, like I was saying, you know, first thing you'd want to do is look at a differential equation and try and identify what type of equation do I have, and then what method is going to help me solve that differential equation. So separable, when we're using separation of variables, first of all, this is only going to apply to first order differential equations. So chapter 1, we're going to first just start with different methods of solving first order differential equations. So it's when we have a first order differential equation, so that that equation can be written as a product of things that depend on x times a product of things that depend on y. So I want to be able to break it up into products. And that's what we had in the previous example. We had t over 3y squared. So I could write that as a product of an expression of t's times an expression of y's. And when you have a differential equation of this form, then you can always try separation of variables. The question is, will you be able to integrate those things? If you can, then great, this method will work. If you can't, then maybe we'll have to try another method. So, so what I'd like to kind of think about below are some examples of differential equations. And so I'm just going to take some quick polls to see how we're identifying the structure here. So I don't necessarily want to solve these. I just want to know whether or not separable differential equation, whether or not this would be separable. So taking a look at A, I'd like you to just respond in whether you think this is separable or not separable. And there's a way of saying definitely or I think as well. And kind of this question that we're all thinking about right now is probably like the most important question to ask yourself before you start solving differential equations. Is let me identify what I'm working with, and then that's going to help me identify what is the best way to solve it. Okay, so take another 10 seconds, please, if you're still gathering your thoughts. Okay, so here were the results. So we had 21 people respond. We had 9. I think it's separable, and we had 11. It's not separable, or I don't think it's separable. So it's a little bit misleading, right? So here we have this written as a sum of x's plus a sum of things that depends on y's. So for those that said not separable, why is this not separable? This is not separable. What's the problem?
I said it wasn't separable because they aren't multiplied together.
That's right.
So if you had a y term multiplied, or if you had a y multiplied by the 3x, you could separate out your y potentially, but you can't separate it out as it is.
That's right. So look up top, we should have f of x times g of x. We have f of x plus g of y. Okay, so we're not trying to separate sums here. We're trying to separate products. So it has to be a product of two things. Yes. And so if we had like 3x times y squared, that would be okay. But up top, that is not going to be separable because what we mean here are products. We could split this up into a product of x's and a product of y's. Okay, any questions about A? Let's try this again. So same question now for B. Do you think B is separable or not? Okay, I will take another 5 seconds, please. Okay, thank you. So here were the results for B. So most people said it is definitely separable, and then we had some less certainty. And so this one is separable. And how can we separate it? Someone want to share how that's separable?
You can factor out a, oh, sorry.
No, go ahead, Marissa.
Okay, you can factor out a y.
Yeah.
So you have y times t squared plus t.
So we can factor out a y, and now we can see that we've got a product, right? So it doesn't necessarily have to be given initially as a product, but once we factor out the y, now I can divide the y by both sides, and then multiply both sides by dt. Go from there. Okay, what about C? We'll speed this up a little bit. Well, I like these polls. These don't take too long. So tell me what you think about C. Is that separable or not? And you'll have some questions like this on your homework. Determine whether this is separable or not. Okay, awesome. Here are the results in case you're curious. So the most common response was separable. This one is separable. And why is that?
You can use properties of exponents to rewrite that as a product, e to the z and e to the w.
Yep, just like we were using on the previous examples.
Yep.
Yeah, and then so now you could bring, not like that, sorry. And we could separate it like that. So yes, in addition to calculus, good time to review some algebraic stuff too, like properties of exponents and logs and things like this certainly come up. What is the property for natural log of x times y?
You can, go ahead.
When you have two things multiplied, it's natural log of x plus natural log of y.
And so now, right, the idea is we're trying to separate the x's and the y's. So when they're both inside the natural log, that's not ideal. So I can separate them into a sum of natural log of x plus natural log of y. Is that going to be separable? That is not, right? For the same reason that A was not separable, because we don't want sums, we want products. So this one is not going to work because here we have a sum, not a product. Okay, and then one last poll. Let's take a look at E. Curious what you think about that one.
Y prime means dy dx, right? And so will there ever be an x prime?
You could have it. Yeah, so if x is the dependent, we'll have times when x depends on t, and we'll have x prime, and that means like dx dt. But the thing that you want to be careful about is when the prime notation is used, it's not as clear what, I mean, it's clear what the dependent variable is, but you need to read the equation to identify what is the independent variable. Yeah. All right, so yeah, so here were the results for the last one, and that's right. So this is separable, and just be aware that these differential equations might not always be given in the dy dx isolated by itself. So before you separate it, you would want to first just kind of solve for dy dx, bring everything else to the other side, and now say, okay, is this a product of x and y's? And it is. Now we've separated that. Okay, any questions? Okay, so now it's time for you all to practice in some groups. So I'm not gonna send you off by yourself, so I'll break us up into smaller groups so you have some people to discuss things with. But question 7, we've got 2 different differential equations. Let's start with A, and if you and your group wrap up A, then feel free to move on to B. But I'd like you to try and solve this initial value problem. So the first thing that you would do is you can ignore the initial condition, find the general solution like we've been doing, and then use the initial condition after you've found a general solution. Okay, welcome back, everyone. Okay, so let's kind of compare notes on how this went. How many groups were able to get A done? Couple? Okay.
Yeah.
Okay, yeah, sorry. I just want to make sure we have time to go through one of these, and then you've got some other ones that you can practice. So it's really a 3-step process here, right? Separate, integrate, try and solve for the dependent variable. I'll just say that's not possible in this one. So if you got stuck at that step, that's fine. Both of these answers are going to have implicit solutions, so we won't actually be able to find an explicit solution. And so the tricky part is the integrate step. That's the step that I think it's good for us to try and review a little bit. So when we separate this, I'll do that part. We would bring our z's over here, and our q over here. And we have a z over here as well. So I think when you separate it, it's going to look like this. And so that z prime is implied that it's dz dq because q is our other variable. And so any questions about that part? And then we want to integrate. So I don't think this one's a little more straightforward, so I'll start there. I've got 1/2 q squared plus c. What happens on the left side? Anyone figure out how to do that one?
You're able to just, sorry?
Oh, sorry. Our group split it apart. So we did z squared over z plus 1 over z, or the integral plus.
Yep, good.
Yeah.
So you can break up sums in the numerator. So we could just break that up. And now we have a sum of 2 power functions, so we can integrate each of those. Right, when the sum is on the bottom, we obviously need to be a little bit more careful. But here we can break up that sum. So this becomes the integral of z plus 1 over z dz. And then on the right side, we've got this 1/2 q squared plus c. And so here we've got 1/2 z squared. And here we have the natural log of the absolute value of z. So in some sense, if you were just asked to find a general solution, you would be done at this stage because there's no way that I can solve that for z. But we want to solve this initial value problem. So now I can plug in these initial conditions at any point. I'm going to do something, what might be nice to do to both sides of this equation just to clean it up a little bit.
Multiply everything by 2.
Yeah, so maybe if we don't like these fractions, right, I can do whatever I want as long as I do the same thing to both sides. And I'm just going to say, if I multiply the arbitrary constant c by 2, I just get some arbitrary constant that I'll call d.
Would it be 2 ln of z?
Yeah, thank you. You're right. I did forget my 2 there. That I need there. Thanks. And at this point, we can plug in our initial condition, which is, this is telling me that when q is equal to 2, we should have z is equal to 1. So I'm going to plug 1 in for z. I get 1 squared plus 2 times the natural log of the absolute value of 1 is equal to q squared. Q is now 2. And then we would solve for d. So I get 1. Natural log of 1 is 0. Is equal to 4 plus d. So therefore, d is equal to -3. So my initial value problem would therefore have a solution of z squared 2 times the natural log of absolute value of z, q squared plus, actually, here we go. And then I can plug in -3 for d. So in this case, that's pretty much as good as we can go. I can't really make that look too much prettier.
When we did ours, we didn't multiply by 2. So we ended up having like z squared over 2, and the natural log of absolute value of z equals q squared over 2. So when we did the constant, we ended up with like -3/2.
Yep. And it's equivalent, right? If you took that equation and multiplied both sides by 2, you would get exactly what I have here.
Okay,
Yeah.
so is it okay to do that? Like you don't have to worry about simplifying it further before
That's fine. Yeah, if you just stopped at this point and said using that form, I'd get 1/2 z squared plus the natural log of z is equal to q squared over 2 minus 3/2. That's the same exact equation as that one over there. Yeah.
Okay, cool.
Okay, so I will, I'll stop here. I will post the solution to bottom one over here if you want to check your work at home. I'll put the solutions to this one and on the last page in case you want some extra practice, but I'll say definitely get some practice with integration. The textbook has problems at the end of each section, and a number of those problems have solutions in the back of the book. So I would say, in addition to the homework, if you want some extra practice, give some of those problems a shot. But okay, sorry, we're out of time. So have a nice week, rest of the week, everyone. If you have any questions about the work, I have office hours tomorrow from 10:30 to 11:30 in the morning. Otherwise, if you want to stick around now, that's fine as well. But if not, have a nice week, and I'll see you on Monday.
Thank you. Have a nice weekend.
Have a nice week.
Thank you.